All right, welcome to this explainer. If you're prepping for the Cambridge IGCSE Physics 0625 exams, I've got something pretty wild to share with you. When you really dig into the data, an interesting pattern emerges. And it turns out that reading the textbook over and over again, that is not what secures a top band grade. Today, we're diving straight into the mechanics of these exams to see how stripping away basic, easily avoidable errors in analyzing motion graphs is the absolute real key to locking in those top marks.
Look, we need to talk about how you're studying right now. It turns out passively rereading textbook definitions for speed, velocity, and acceleration is actually a massive waste of highly valuable study time. I mean, sure, memorizing that acceleration is the rate of change of velocity might make you feel super productive in the moment, but it does absolutely nothing for your ability to extract complex data from a multi-stage motion graph when you're sweating under intense exam conditions. Cambridge examiners don't just test your memory, right? They test your application, and relying on passive reading is literally setting a trap for yourself.
And the cost of falling into that trap? It is incredibly high. A single misinterpretation of a motion graph can instantly cost you up to 4 marks on a structured question. To put that into perspective, in the Cambridge 0625 grading system, dropping 4 marks on just one question can literally be the difference between an A star and an A, or an A and a B. It just drops you down a full grade bound in a blink. Worse, getting confused by the graph means you're going to spend 5 extra minutes second-guessing your calculations, which means you're going to run out of exam time before you even reach the really high-mark physics questions at the back of the paper.
Which leads us to a kind of absurd question, right? Why do simple, straight lines on motion graphs trick like 80% of students? I mean, it's just a straight line. But the specific trap almost everyone seems to fall into is just failing to check the y-axis. Students constantly, and I mean constantly, mix up distance time graphs with speed time or velocity time graphs. A straight diagonal line on a distance time graph means constant speed. But that exact same straight diagonal line on a velocity time graph, that means constant acceleration. Visually, they look identical, but conceptually, they are worlds apart. And examiners know exactly how to exploit this visual trick to test if you actually understand what you're looking at.
Now, while digging through examiner reports, I found a specific phrase examiners use in their questions. It's basically a hidden clue that hands you the answer on a silver platter. Honestly, it's probably the single most important examiner clue in the entire 0625 syllabus. But before I give you that clue, we have to understand the underlying framework. Because without the framework, the clue honestly means nothing.
Okay, let's dive into this. Section 1, the 4-step exam framework, from learner to top band.
So the methodology we uncovered breaks down into 4 parts. Step 1 is identifying the concept. Ask yourself, what physics principle is actually being tested here? Step 2, gather evidence and data directly from the graph. Don't just talk generally. Use the actual specific numbers provided on the axes. Step 3 is where you apply scientific reasoning. You need to connect the data to the concept using your physics formulas. And finally, step 4, use examiner wording. Package your answer using the precise terminology that the mark scheme demands. This 4-step method forces you to slow down, analyze the specific situation in front of you, and construct an airtight answer that examiners absolutely love to grade.
All right, quick pause. I want you to think about this classic answer written by thousands of IGCSE students every year. The line goes up, so it's accelerating. Can you spot the error based on the 4-step framework we just talked about? Like, what is missing here? Why would a strict examiner give this 0 marks, even if the object actually is accelerating? Let's compare that flawed answer with a true top band response. Ready? The constant positive gradient indicates constant acceleration of 2.5 meters per second squared. The difference is night and day. The flawed answer is super vague, it uses non-scientific language like goes up, and it references absolutely no data. But the top answer? It doesn't just describe a picture, it analyzes mathematical relationships and proves them with hard data. This is that transformation from basic concept to solid evidence that gets you full marks. And this brilliantly illustrates how the framework functions in practice. It hits the concept by recognizing that the slope of the line, the constant gradient, is the key feature. It extracts the data by calculating the actual value as 2.5 meters per second squared, and it applies scientific reasoning by explicitly stating that this gradient represents acceleration. By structuring your answer exactly like this, the examiner literally has no choice but to award you maximum points. Every single hidden box on their mark scheme is checked off.
This whole thing really hit home for me when I read an incredibly authoritative quote straight from a Cambridge examiner's report. They wrote, "Candidates frequently confuse the gradient of a distance time graph with a speed time graph, losing all marks for subsequent reasoning. Notice the brutal severity of that statement, losing all marks. It's a complete domino effect. Misidentified in the graph means your gradient calculation is wrong, so your subsequent force calculation is wrong, which means your final energy calculation is wrong. It is a fatal, almost painfully cruel error to make.
So, the crucial point is, how do we avoid this fatal error? Well, that brings us right back to that examiner clue I mentioned earlier. Whenever a question prompts you to state the feature of the graph that shows, they are handing you a massive gift. This specific command phrase tells you exactly what your next move should be. They don't want a paragraph of text, they want one of two very specific geometric features. Here's what that translates to in plain English. When they ask for the feature, they mean either the gradient, which gives you the acceleration on a velocity-time graph, or the area under the curve, which gives you the total distance traveled. That's the whole secret. Knowing this specific definition immediately unlocks the rest of the question for you. You don't have to sit there sweating, guessing if you should use kinematics formulas like v equals u plus at, or if you should do a geometry calculation. The word feature is screaming at you to either calculate the slope or calculate the area.
Now let's move on to Section 2, escalating the stakes, calculating the area.
To conquer this next part, we just apply that same framework directly to our data analysis. Step 1, identify the geometric shape. Take that complex graph and split it into simple triangles and rectangles. Step 2, read your axes units carefully. Are they in seconds or minutes? Are they in meters per second or kilometers per hour? Step 3, calculate the area of those shapes, keeping in mind that this area literally equals the distance. And Step 4, state your final units clearly. By strictly following these steps, what looks like a terrifying, overly complex shape just turns into a couple of simple, bite-sized math problems.
But wait, there is a hidden trap here, and it revolves around the number 0. 0 is exactly the number of marks you'll be awarded if you do all that beautiful math, but completely forget to square the seconds in your final unit for acceleration, like if you write m/s instead of m/s squared. 0 is also what you get if you misread the axis scale. For example, assuming one tiny grid square is worth 1 unit when it's actually worth 0.2 units. Honestly, it's almost cruel how examiners intentionally set up these scale traps. A silly unit error or a misread axis can easily turn a completely perfect calculation into big fat 0 marks. So, we've covered straight lines, constant gradients, and basic areas, but here is the ultimate cliffhanger for you. What happens when the acceleration isn't constant and the graph curves? A curved velocity time graph means you can't just pick 2 points and calculate a simple slope anymore. The acceleration is literally changing every single second. The standard rules we just uncovered suddenly fall apart, and trying to force them onto a curve will completely derail the question. Because of this, your logical, mandatory next step is to move beyond basic straight lines. The advanced, high-tier content requires you to learn how to draw tangents and totally master variable acceleration data analysis. This is the stuff that truly separates the average students from the elite. Conveniently, mastering that is exactly how we solve this whole curved graph dilemma. You now know exactly how to extract perfect data from straight lines to guarantee your marks, but are you brave enough to face the curves that define the absolute hardest papers in the 0625 syllabus? Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. I'll see you in the next explainer to find out